In the grand tapestry of scientific discovery, some threads shine brilliantly for a moment only to fade, while others weave themselves slowly and quietly into the fabric of our understanding. The story of cold fusion is one of those brilliant, fleeting threads that promise to reshape our world. It began not in a colossal particle accelerator or a government super-laboratory, but on a humble tabletop at the University of Utah. On March 23, 1989, two respected chemists, Martin Fleischmann and Stanley Pons, held a press conference that sent shockwaves through the global scientific community. They announced they had achieved nuclear fusion, the very power source of the stars, in a simple glass jar at room temperature. Their claim was as audacious as it was revolutionary. Imagine the scene: a small electrochemical cell, not much more complex than a high school science project. Inside, an electrode made of palladium, a silvery white metal, was submerged in a bath of heavy water. Heavy water is a special form of H2O where the hydrogen atoms are replaced by deuterium, a heavier cousin with an extra neutron in its nucleus. When they passed a simple electric current through this setup, Fleischmann and Pons observed something astonishing. The cell began to produce a remarkable amount of excess heat, far more energy than could be explained by any known chemical reaction. It was, they claimed, the signature of atoms fusing together, releasing a sliver of their immense nuclear energy not with a bang, but with a gentle, sustained warmth. This wasn't just another incremental step in science, it was a quantum leap, or so it seemed. For decades, physicists had been chasing the dream of controlled fusion, a source of limitless, clean energy. Their path involved building gigantic, multi-billion-dollar machines called tokamaks, designed to heat hydrogen gas to temperatures hotter than the core of the sun, hundreds of millions of degrees, to force atomic nuclei to merge. Fleischmann and Pons were suggesting that this monumental effort might be unnecessary. They proposed that the unique crystalline structure of palladium could act as a sort of quantum vice, squeezing deuterium nuclei so tightly together that they could overcome their natural repulsion and fuse without the need for stellar heat and pressure. The implications were staggering. If true, their discovery meant that the awesome power that fuels our sun could be tamed and miniaturized. It offered a vision of a future free from the pollution of fossil fuels, the dangers of nuclear fission, and the geopolitical conflicts over energy resources. The universe's ultimate power source, it seemed, was not locked away in distant stars or complex machines but was accessible right here on Earth, in a simple apparatus you could hold in your hands. This announcement was not just a scientific paper, it was a declaration that humanity had perhaps found the key to its long-term survival and prosperity, a spark of hope contained within a jar of water. The news of cold fusion exploded across the globe with the force of a supernova. It wasn't confined to the dry academic pages of scientific journals, it was front-page news, the lead story on evening broadcasts, and the talk of every dinner table. The media, captivated by the David and Goliath narrative of two chemists upending the world of physics, painted a vivid picture of a utopian future just around the corner. Journalists and commentators hailed the discovery as one of the most significant moments in human history, on par with the discovery of fire or the splitting of the atom. The promise was intoxicating. An era of clean, cheap, and virtually inexhaustible energy was dawning. The vision sold to the public was nothing short of a technological paradise. Experts and futurists speculated about small silent power units in every home, making the sprawling, centralized grid of power plants obsolete. Cars would run on a few drops of water, their emissions a harmless puff of steam. The specter of climate change, driven by the carbon dioxide pumped into our atmosphere from burning coal, oil, and gas, would vanish. The dangerous, long-lived radioactive waste produced by conventional nuclear power plants would become a relic of a primitive past. This wasn't just an energy solution. It was a solution to some of humanity's most pressing environmental and political problems, all born from a simple desktop experiment. This wave of excitement wasn't just media hype, it triggered a frantic race among scientists, governments, and corporations. The state of Utah quickly allocated millions of dollars to establish a dedicated cold fusion research institute. Congress held urgent hearings, with lawmakers eager to understand how the United States could secure its leadership in this revolutionary new field. Investment poured in from venture capitalists and private companies, all hoping to get in on the ground floor of a technology that promised to be more lucrative than the oil industry itself. In laboratories from MIT to Tokyo, researchers scrambled to replicate the Fleischmann-Pons experiment, working day and night in the hope of confirming the miracle. It felt as though the world was holding its collective breath, standing on the precipice of a new age. The very term cold fusion entered the popular lexicon, becoming a shorthand for a scientific miracle that could solve all our problems. It represented a fundamental shift in our relationship with energy, moving from a model of scarcity and pollution to one of abundance and cleanliness. The initial announcement by Fleischmann and Pons was more than just a scientific claim. It was a beacon of hope, illuminating a path toward a cleaner, brighter, and more prosperous future for all of humanity. For a few brief, exhilarating months, it seemed that the stars had come down to Earth. Just as quickly as the fire of excitement had been lit, a cold wave of skepticism began to wash over the scientific community, particularly from the world of physics. While the public and politicians were swept up in the dream of limitless energy, physicists looked at the claims with a trained, critical eye. They knew the immense difficulty of forcing two atomic nuclei to fuse. Nuclei are both positively charged, and repels. Overcoming this fundamental force, known as the Coulomb barrier, requires tremendous energy, the kind found in the heart of a star, or a thermonuclear bomb. The idea that this could happen in a beaker of water at room temperature seemed to fly in the face of a century of established nuclear physics. The first major red flag was the lack of expected byproducts. According to everything we know about nuclear fusion, when two deuterium nuclei combine, they should produce telltale signs of the reaction. The most common fusion pathways release either a high-energy neutron and a helium-3 nucleus, or a proton and a tritium nucleus. Furthermore, these reactions should unleash a torrent of gamma rays, a form of highly energetic radiation. Physicists immediately pointed out that if the amount of heat Fleischmann and Pons were reporting was truly from fusion, the experiment should have been emitting a lethal dose of neutrons. The two chemists, however, were still alive and well, and their detectors had registered only a negligible amount of radiation. This glaring discrepancy led to a frantic, worldwide effort to replicate the experiment. Top laboratories, including MIT, Caltech, and Harwell in the UK, poured resources into building their own versions of the Fleischmann-Pons cell. The results were devastating for the proponents of cold fusion. The vast majority of these highly sophisticated experiments found nothing. They measured no excess heat beyond what could be accounted for by experimental error, and they certainly detected no significant neutron emissions. A few labs did report some small, puzzling anomalies. A tiny blip of heat here, a flicker of neutrons there, but these results were sporadic, weak, and could not be reliably reproduced even within the same laboratory. The failure to independently and consistently replicate the results was the nail in the coffin for many mainstream scientists. Science, at its core, relies on reproducibility. A discovery is only considered real if other qualified researchers, following the same procedure, can achieve the same outcome. By the end of 1989, the consensus was hardening. Cold fusion was likely a case of experimental error, wishful thinking, or perhaps an unknown chemical effect, misinterpreted as a nuclear one. The initial euphoria gave way to bitter disappointment and recrimination. The scientific establishment, feeling that its standards had been bypassed by a premature press conference, largely dismissed cold fusion as pathological science, a cautionary tale of how not to conduct research. By the early 1990s, the term cold fusion had become toxic in the scientific world. It was synonymous with failure, public embarrassment, and pseudoscience. Mainstream funding evaporated, prestigious journals refused to publish papers on the subject, and any researcher associated with it risked their career and reputation. For most, the story ended there, a curious but closed chapter in the history of science. However, for a small, dedicated group of scientists who had witnessed fleeting but tantalizing anomalies in their own labs, the mystery was not solved. They believed that while the grand claims of Fleischmann and Pons may have been overstated, something real and unexplained was happening within those metal lattices. To escape the stigma and continue their work, these researchers made a strategic decision to rebrand their field. They moved away from the loaded term cold fusion, which implied a specific and unproven mechanism. Instead, they adopted a more cautious and descriptive name, low-energy nuclear reactions, or LENR. This new terminology served a dual purpose. First, it distanced them from the controversy and media circus of 1989. Second, it more accurately reflected the nature of their investigation. They were no longer promising a miracle energy source, they were methodically studying a set of unexplained phenomena that appeared to be nuclear in origin but occurred at low energies. Under the banner of LENR, the research retreated from the public spotlight and went underground, carried on in smaller, often privately funded laboratories in the United States, Italy, Japan, and Russia. This shift marked a change in philosophy. The goal was no longer to build a power plant in a year, but to gather high-quality, reproducible data. The focus narrowed to the most persistent and well-documented anomaly, the production of excess heat. Researchers worked to design more sophisticated calorimeters, devices for precisely measuring heat, to prove beyond any doubt that the energy they were observing was not a result of measurement error or unknown chemical sources. This new phase of research was slow, painstaking, and often isolating. Scientists in the LENR field formed a tight-knit but marginalized community, holding their own conferences and publishing in a small number of specialized journals. They faced constant skepticism from the mainstream and struggled for funding and recognition. Yet, they persisted, driven by the conviction that the data, however strange and difficult to reproduce, pointed toward a new and potentially revolutionary area of physics. The transition from cold fusion to LENR was more than just a name change, it was a strategic retreat, a regrouping of forces to fight a long-term battle for scientific legitimacy. Decades after the initial uproar, the core mystery of LENR endures, centered on a handful of persistent and perplexing anomalies that just refuse to disappear. The most significant and well-documented of these is the phenomenon of anomalous excess heat. In numerous experiments conducted by different teams around the world, researchers have consistently reported generating more thermal energy from their devices than the electrical energy they put in. This isn't a small discrepancy. Some experiments have claimed to produce watts or even kilowatts of excess power, sometimes for days or even weeks on end. Skeptics have long argued that this is simply a result of poor calorimetry, the difficult art of measuring heat flow. However, as experimental techniques have become more sophisticated, this explanation has become harder and harder to sustain. Proponents of LENR argue that after accounting for every conceivable chemical reaction and potential source of measurement error, there remains a surplus of energy that really defies conventional explanation. This ghost in the machine is the bedrock of the entire field. Without excess heat, there is no mystery. But with it, researchers are forced to consider unconventional energy sources. The energy released in these experiments, they contend, is far greater than what can be produced by breaking any chemical bond, suggesting that the origin must be nuclear, where vastly greater amounts of energy are stored within the atom's core. Beyond just heat, some LENR experiments have reported another tantalizing piece of evidence: the production of new elements. This process, known as transmutation, is a hallmark of nuclear reactions. For example, when a neutron strikes a nucleus, it can transform it into a different isotope, or even a different element entirely. In the context of LENR, researchers have analyzed the surface of palladium or nickel electrodes after an experiment, and found traces of elements that were not there to begin with. They've reported shifts in the isotopic ratios of elements within the metal, another potential fingerprint of nuclear processes that cannot be created by chemical reactions alone. One of the most compelling pieces of evidence for the nuclear case is the detection of helium-4, the same stable helium isotope produced in the fusion reactions that power the sun. In a series of carefully controlled experiments, researchers have measured the amount of excess heat produced and simultaneously collected the gases released by the cell. They have found a strong correlation between the amount of heat generated and the amount of helium-4 produced. This quantitative link suggests that the heat is the direct result of a nuclear reaction that creates helium as its ash. For LENR proponents, this heat-helium correlation is powerful evidence that they are indeed witnessing a new form of nuclear process. While the evidence for excess heat and nuclear byproducts like helium keeps the field alive, it also presents its greatest paradox, one that fuels the deep-seated skepticism of the mainstream physics community. The central problem is the profound lack of dangerous radiation. According to our well-established understanding of nuclear physics, fusing deuterium nuclei should be a messy and violent affair. The immense energy released when the nuclei merge has to go somewhere, and it typically does so in the form of high-energy particles like fast neutrons and powerful gamma rays. These particles are not subtle. They are easily detectable and extremely hazardous to living things. If the heat reported in LENR experiments were generated by the known fusion reactions that physicists study in high-temperature plasmas, the neutron emissions would be so intense that they would deliver a lethal radiation dose to anyone in the same room within minutes. The experimental setup itself would become intensely radioactive. Yet, one of the most consistent findings across all LENR experiments is that the radiation levels are at or near the natural background level. The neutrons that are detected are incredibly rare, billions of times fewer than what conventional theory predicts for the amount of heat being generated. This discrepancy is often called the heat without radiation problem, and it is a fundamental barrier to acceptance. To a mainstream physicist, this is not just a puzzle, it's a violation of the known laws of nature. The principles of energy and momentum conservation are cornerstones of physics, and it's not clear how a nuclear reaction could release its energy primarily as gentle heat, without also ejecting energetic particles. It would be like claiming to have a fire that produces warmth, but no light, and no smoke. This apparent contradiction is the primary reason why many physicists dismiss the entire field out of hand. They argue that extraordinary claims require extraordinary evidence, and claims that seem to violate fundamental physical laws require a level of proof that LENR researchers have yet to provide. Proponents of LENR are, of course, keenly aware of this paradox. They don't dispute the measurements of mainstream physics. Instead, they propose that the mechanism at play must be something entirely new and different from hot fusion. They theorize that the unique, dense environment of the metal lattice somehow facilitates a different kind of nuclear reaction, one that bypasses the typical high-energy particle pathways. The energy, they suggest, might be transferred directly to the surrounding lattice, causing it to vibrate and generate heat, rather than being thrown off as a high-speed neutron. This explanation, however, remains a hypothesis without a solid theoretical foundation, leaving the paradox of clean heat as the central unresolved mystery of LENR. The profound disconnect between the experimental observations of LENR and the predictions of established nuclear theory has forced researchers to think outside the box. If the anomalies are real, they imply that our current understanding of nuclear physics might be incomplete. The search for a theoretical explanation for LENR is a journey into the speculative frontiers of science, an attempt to build a new framework that can accommodate these strange results. Over the years, dozens of theories have been proposed, though none has yet gained universal acceptance, even within the LENR community itself. These theories range from extensions of known physics to far more exotic and revolutionary ideas. One of the most enduring lines of thought centers on the special properties of the metal lattice. In a solid metal like palladium or nickel, atoms are packed into a highly ordered, repeating crystalline structure. When deuterium is loaded into this lattice, the deuterium nuclei are squeezed into the tiny spaces between the metal atoms. Some theories propose that within these confined quantum spaces, the rules of the game change. The collective electromagnetic fields of the lattice might work to shield the positive charge of the deuterium nuclei, effectively lowering the repulsive barrier between them and allowing them to approach each other much more closely than they could in free space, perhaps enabling a novel form of fusion. Another group of theories speculates about the formation of novel ultra-dense particles or states of matter. For example, some have proposed that, under the intense pressures and electromagnetic fields inside the lattice, clusters of deuterium nuclei might collapse into a transient, exotic state. This hypothetical state could then decay through a nuclear process that releases its energy collectively to the lattice as heat, rather than through the violent emission of a single high-energy particle. Other theories involve complex interactions with electrons, suggesting that a collective heavy electron could form which would neutralize the charge of the nuclei and allow them to fuse easily, similar to a known but impractical process called muon-catalyzed fusion. Ultimately, all these theories are attempts to explain the two key features of LENR, the generation of nuclear-level energy and the absence of expected radiation. They propose mechanisms by which the enormous energy of a nuclear reaction can be thermalized, that is, distributed as low-grade heat among countless atoms in the lattice instead of being released in one explosive burst. While these ideas are intellectually stimulating, they remain highly speculative. Without a predictive and testable theory, LENR remains a collection of unexplained observations rather than a fully fledged scientific field. The quest for a working theory is as crucial as the quest for reproducible experiments, as it is the bridge that could one day connect this strange new world to the continent of known physics. After decades in the scientific wilderness, the field of low-energy nuclear reactions is experiencing a quiet but significant resurgence. Today in 2025, the landscape is markedly different from the chaotic aftermath of 1989. The wild promises of imminent energy revolutions have been replaced by a more sober and methodical approach. The research is no longer just the domain of a few marginalized pioneers. A new generation of scientists, armed with far more sophisticated diagnostic tools and a better understanding of materials science, is taking a fresh look at the phenomenon. This reawakening is being cautiously supported by mainstream institutions that would have shunned the topic a decade ago. A key driver of this renewed interest is the slow but steady accumulation of higher quality data. Modern experiments are designed with meticulous attention to eliminating errors. Researchers now use multiple redundant methods for measuring heat, employ state-of-the-art mass spectrometers to detect nuclear ash like helium, and use sensitive radiation detectors to continuously monitor for any emissions. This focus on rigorous methodology has produced results that are harder to dismiss as mere error. While perfect reproducibility remains a challenge, the signal-to-noise ratio has improved, with some experiments demonstrating sustained excess heat with a high degree of certainty. This progress has not gone unnoticed. Major government and military research agencies in the United States, Europe, and Asia have begun to quietly fund LENR research once again. Organizations like ARPA-E, the Advanced Research Projects Agency Energy in the United States, have sponsored programs aimed at definitively proving or disproving the existence of anomalous heat effects in metal-hydrogen systems. These agencies are not necessarily betting on a new energy source, rather, they are performing due diligence. The potential payoff, however small the probability, is simply too large to ignore completely. If there is even a 1% chance that a new, clean, energy-dense power source is achievable, it is a matter of national security and economic competitiveness to investigate it. Furthermore, the research has expanded beyond the original palladium-deuterium systems. Scientists are now exploring a wide range of materials and stimulation methods. Nickel-hydrogen systems have become particularly popular, as nickel is far cheaper and more abundant than palladium. Some groups are experimenting with novel nanomaterials, believing that the unique properties of materials at the nanoscale might enhance the effect. Others are using external triggers, like lasers or acoustic waves, to try to stimulate reactions in a more controlled and predictable way. This diversification of approaches increases the chances of a breakthrough, and signals a field that is maturing from a single controversial experiment into a broader scientific inquiry. Today, the story of cold fusion, now reborn as LENR, stands at a critical crossroads. The field remains deeply polarized, a battleground between unwavering skepticism and persistent belief. On one side, the majority of the scientific community continues to view the subject with suspicion, seeing it as a distraction from more promising avenues of energy research. They point to the ongoing struggles with reproducibility, the lack of a coherent theory, and the apparent violation of fundamental physical laws as insurmountable obstacles. For them, LENR is a ghost story told by scientists, a tale built on decades of ambiguous data and wishful thinking that diverts precious resources and intellectual capital. On the other side are the proponents, a growing minority who argue that ignoring the persistent evidence is a greater folly. They see a consistent pattern of anomalies, excess heat, helium production, and transmutations that has survived decades of scrutiny and improved experimental methods. They contend that science has a duty to investigate the unexplained, not to dismiss it simply because it is strange. To them, the lack of a theory is not a reason for dismissal, but a call for more creative thinking. They remind us that many revolutionary discoveries, from electricity to quantum mechanics, began with baffling observations that defied the conventional wisdom of their time. The potential impact of a proven linear technology is difficult to overstate. If the phenomenon is real and can be harnessed, it would represent the single greatest technological breakthrough in human history. It would offer a solution to the twin crises of climate change and energy security. A world powered by LENR would be one with decentralized, abundant, and clean power, free from greenhouse gas emissions and long-lived radioactive waste. It would fundamentally reshape our economy, our geopolitics, and our relationship with the planet. The tantalizing possibility of this future is what keeps the flame of LENR research burning, despite the scientific headwinds. Ultimately, the future of LENR will be decided not by debate, but by data. The central question remains, can researchers develop an experiment that is unambiguously reproducible, one that can be sent to any competent lab in the world and produce the same anomalous results on demand? Achieving this golden standard is the holy grail for the field. Until that day comes, LENR will remain a fascinating, controversial, and high-stakes gamble. It may yet prove to be the energy revolution that never was, a footnote in the history of science. Or just possibly, it could be the quiet dawn of a new era, a revolution that has been simmering on the fringes of science, waiting for its moment to change the world forever. The universe is under no obligation to conform to our expectations.